For part C, we're now going to find any points of inflection. And to do this, we need to work with the second derivative of our function. So if we look back, I'll just write down what we had here. F prime of x was 4x cubed minus 12x. So to get f double prime, we're going to take the derivative of this guy and get 12x squared minus 12. So we now want to find critical points for f double prime of x. Critical points, places where f double prime of x is equal to 0. So let's take 12x squared minus 12, set it equal to 0, and it might help to do a little bit of factoring here. Let's pull out a factor of 12. Okay, and then notice that x squared minus 1 is a difference of squares. So we actually have x minus 1 times x plus 1 there. So now that's fully factored. Okay, so we get a couple of different critical points here. X equal 1 is one of them. X equal negative 1 is another. So now we're going to draw a similar kind of chart to what we had in part B. We'll throw our critical points on there. And again, the idea is that these x values, these are the only places where f double prime of x can change signs. So what that means is that if we check a value of f double prime in this first interval, say we plug in -2 here, that's going to tell us the sign of f double prime on that entire interval, because the sign cannot change at any x values except at these critical points. Okay, so we'll make a little chart here. We will plug in some numbers for each of our intervals here, and we'll write down the sign of f double prime of x, and we'll also write down what that means for our function. We can make a little chart here. So choosing -2 to go into our second derivative, you can check that you get a positive value for f double prime. And what that means for our function is that it's concave up. I'm just going to write this CU for short. So it means our function has the shape of, let's say, a cereal bowl, a right side up bowl that you might eat your morning cereal out of. So concave up looks like that. It has that kind of shape everywhere in that interval. If we move into the middle interval, let's say plugging in 0, for example, you can check that the second derivative comes out negative. That means our function, f of x, is concave down. It now looks like an upside down bowl. And in this third interval, maybe we choose the x value 2 to plug into our second derivative. You can choose any x value that's in this interval here to plug in, and you can check second derivative comes out positive. So that tells us our function is concave up, again, on that entire interval. All right, so there's our chart redrawn there. Now to answer the question about points of inflection. Points of inflection are places where the concavity changes. So where the function moves from concave up to concave down, or vice versa. So we do have a point of inflection at the x value -1, and we have another point of inflection at the x value 1. So 2 points of inflection. Now to get the y values, remember we're going to use these points here when we're sketching the curve. So the y values have to come from the original function. We're going to plug 1 into our original function. That comes out to -5. So 1 common -5 is point of inflection. Another point of inflection is at -1, -5. Again, that -5 comes from plugging into our original function. So that is f of -1. Okay, very last part of the question, we are now going to sketch our graph. We are going to label our axes, and we're going to indicate some scale on our axes. Now, in terms of the y-coordinates, we need to go down as far as -9, according to the points that we found. So let's say -9 is there. -5 will be another important y value if we look back at the points that we found. And the x values that will be important, we'll need to go as far over as about +2 and -2 to get all our points on there. So let's just make that look a little bit more even there. All right, so with that, we make sure that we've got enough space to get all our points on there and that we understand the scale on both axes. So that looks good. Now, the points that we need to plot, we found the y-intercept was 0, 0. We found some relative minimum and relative maximum points. So those were -√3, -9. So right down about there. Also +√3 and -9. So about there. And 0, 0 was another one of those relative extrema. 0, 0 was a relative maximum. We've also got a couple points of inflection that we can put on there. So we need one at 1, -5. And I'm actually going to move this -5 here. Maybe we could indicate the scale somewhere else, like up here at -1, just so that we can fit in this point nicely. So there's -1, -5. Okay, so those are the 5 points that we found through the course of the problem. Now, to take a look at the increasing, decreasing behavior, we said that the function was decreasing down to the x value -√3. I'm just going to draw this in really roughly here because we will use the concavity a little bit later on to make a better picture. Then we said it was going to be increasing until we hit the x value 0. So it's going to be increasing all the way up here. Then it's decreasing again until we hit the x value √3. So decreasing all the way through here and then increasing beyond that. Okay, so we're getting this kind of W shape is what we're seeing. But now to make a really good sketch, we need to bring the concavity into the discussion. So the graph is supposed to be concave up until we hit the x value -1. So in other words, until we get to this point, the graph should be concave up. All right, so that means it's going to have this kind of a shape. It's going to be coming down. It's going to look like a right side up bowl right through here until this point. Then the graph becomes concave down. So now it's curving slightly differently. Now it looks like an upside down bowl all the way over till the x value 1, and then it starts to look concave up again. So now it's got this kind of a shape. Okay, and at the two ends here, you can just throw arrows on your graph if you like. And I'm noticing that I've just drawn it slightly differently on the two sides, although in fact the graph would be symmetric. So I'm just going to try to reflect that in the picture. Should look roughly even on the two sides. And there we go. So now we've got a sketch. My hand was a little bit shaky there, but we've got a sketch that reflects the increasing, decreasing behavior. Okay, it also reflects the concavity, and it's got all the points on here. So now that we've actually laid down our sketch, let's just label our points. Can use arrows to get the labels just out of the way here that we like. We got the axes labeled, we've got the points labeled, we've got scale indicated on both of our axes, and then to draw the actual curve, we've used the increasing, decreasing behavior, as well as the concave up, concave down behavior.